what hopefully we can get to is, first of all, we're going to talk about just listing the terms of a sequence and what a sequence is. We're going to try to determine whether a sequence converges or diverges. We're going to be writing a formula for the nth term of a sequence, and we're going to try to get to, hopefully today, using properties of a monotonic sequence and a bounded sequence. So what's a sequence? Well, just like in everyday life, when we say something sequential, it's got an order to it. In mathematics, a sequence is basically a function where you map the number 1 to the first term of some series of numbers. I should say sequence of numbers. So the number 1 matches up with whatever A1, the first term of the sequence is. 2 matches up with A2, and so on. We generally use this subscript notation rather than function notation for sequences, but it is a function. Again, we call A1, A2, A3 the terms of the sequence, and A sub n would be referred to as the nth term of the sequence. So don't confuse that with the notation that we use to represent the entire sequence. So when you put the little curly brackets around it, that's denoting the entire sequence, not the nth term. So the name of the whole sequence is bracket A sub n close bracket. So we define sequences in a variety of ways. One way is using a formula. And so, for example, in this case, it says the terms of the sequence A sub n equals 3 plus negative 1 to the n are. So what we're going to do is just plug in the values of n. Remember, sequences are always based on a first term, a second term, a third term, and so on. And so oftentimes we're just plugging in to some formula the numbers 1, 2, 3, and so on. So in this case, we would have for the first term A sub 1, plugging in 1 for n, we would have 3 plus negative 1 to the first power, which is 3 minus 1, or 2. And then for the second term, we would have 3 plus negative 1 to the second power, which is going to be 3 plus 1, or 4. And then the third term would be 3 plus negative 1 to the third power, which is going to be 3 minus 1, or 2 again. And the fourth term would be, that's supposed to be a 4. That's going to be 3 plus negative 1 to the fourth power. And again, that's going to be 4. So you can kind of see what's going to happen here. It's just going to keep alternating 2, 4, 2, 4, 2, 4. So that's an example of one sequence. Another one we might look at might be something like this. Let me erase some of this stuff here. Okay, so we're going to list out some terms of the sequence B sub n. So they're telling us the nth term of the sequence is n over 1 minus 2n. So again, plugging in n equals 1, we see that b sub 1 is 1 over 1 minus 2 times 1. So that's 1 over 1 minus 2, or 1 over negative 1 is negative 1. And b sub 2, the second term in the sequence is going to be 2 over 1 minus 2 times 2. And that's going to be 2 over negative 3. 1 minus 4 is negative 3. And then b sub 3 would be 3 over 1 minus 2 times 3, which is 3 over 1 minus 6, or negative 3/5. Okay. So just a couple examples of some sequences. Another one, you'll notice you commonly will have powers. Sometimes the n is in the power, like in this case. So for this sequence C sub n, our C sub 1 term is going to be 1 squared over 2 to the first minus 1. So that's going to be 1 over 1 c sub 2 is going to be 2 squared over 2 to the second minus 1, which is 4 over 4 minus 1, or 3. C sub 3 is going to be 3 squared over 2 to the third minus 1, which is 9 over 8 minus 1 is 7. And you could continue in that way. I'm just going to check real quick to see if anybody's got any issues. So again, type into the chat bar if you have any questions or having any technical problems like an echo or anything like that. Okay. Let's go on. Okay, another type of sequence that's not defined just by plugging into a formula is called a recursively defined sequence. Let me clean this up a little bit here. So in this next example, we're going to look at a recursively defined sequence, meaning that each term is defined by the previous term. In a recursively defined sequence, you need to know the first term in order to get things rolling. So here they're telling us that this sequence dn, the first term d sub 1 is 25. And so now we do have a formula, but the formula you see relies on the next term, d sub n plus 1, being determined by the previous term, d sub n. For example, if we wanted d sub 2, right, that's d sub 1 plus 1, we would need to take d sub 1 and subtract 5 from it. So d sub 2 is actually just 25 minus 5. If you can see my 2 here. Hold on. So we have the first term, d sub 1, 25, minus 5 gives us 20. But then the third term is going to be the second term, d2 minus 5. So that's going to be 20 minus 5, which is going to be 15. And so you can see that we're just going to keep taking the new term that we found, subtract 5 from it to get the next term. So d4 would then be 10. And it's going to continue in that way. Now, sometimes it helps when we're working with sequences to think of them in terms of graphs. So this is actually an example from our Larson textbook. It asks us to match the graph with the sequence. So we're given the nth term of several sequences, and we want to figure out which one's which. So for example, let's start with number 9. We have the nth term, a sub n equals 10 over n plus 1. So the first term is going to be 10 over 1 plus 1, or 2, which is 5. Okay, and so what that means is that if we were to graph the sequence, we would see a point, a dot at 1, 5. And so for example, here A has the point 1, 5, C has a point 1, 5. So it's going to be one of those two. Let's keep going with our sequence. So the second term of the sequence, actually let me move this, make a little room. Come on, there we go. The second term of the sequence is going to be 10 over 2 plus 1, or that's going to be 10 thirds, or 3 1/3. So if you look at graph A, we have at the x value 2, the input value 2, it's an n value actually in this case, but it's just like x and y. 2 is up above where we started. This sequence is decreasing, it looks like, not increasing. So in other words, the second term, the second term of the sequence is less than the first term, so it looks like it's going down. And if you look right here, it looks like this one does match up to about 3.5. If you wanted to, you could check another and just make sure, but it looks like that 9 matches up with graph C. Okay, again, this is what's called a decreasing sequence, just like we had decreasing functions before. Let's check 10. So for number 10, we have a sub n equals 10n over n plus 1. So a sub 1 would be 10 times 1 over 1 plus 1, which would be 5. So most likely this is going to be sequence A, because it goes through 1, 5. That's the only other one besides C that does. Let's see if this actually does increase as the graph shows. So plugging in 2, we'd have 10 times 2 over 2 plus 1. That's going to be 20/3, which is going to be almost 7. It's going to be 6 and 2/3. So yeah, it's definitely increasing. The second term is higher than the first. It's got to be A over there. Okay, let's look at what's happening with sequence 11. This is one of my favorite sequences. So this is an example of what's called an alternating sequence, because when you raise -1 to a power, if it's an odd power, you get a negative, but if it's an even power, you get a positive. So what happens is that A1 is -1, A2 is 1, A3 is -1, and so on. And so where do we see that? That would be D. You see how at 1 we are down, and then 2 we're up, and 3 we're down, and 4 we're up. And it's always alternating between 1 and -1 here. Okay, number 12 is also an alternating sequence, but it's not just the sign that's changing as it was in number 11. The values of the base are changing as well. So what's going to happen with that one? Number 12 is going to match up with B, the only remaining graph here. Okay, and what's going to happen is, since we're dividing each nth term by n, you're going to get fractions. So you're going to get -1, and then you're going to get +1/2, and then -1/3. So you've got -1, +1/2, -1/3, +1/4, -1/5, +1/6, -1/7, and so on. Notice these are coming in toward the axis, but from two different sides. So it's still alternating because it's going opposite sides of the axis, but we see that the values are getting closer together over time, or over the course of the sequence. All right, so one of the other things that we're going to want to do, besides just matching a sequence with its graph, is we're going to identify what appears to be the next two terms in a sequence given the first few terms. So we're going to start with this one, part A. We're going to do the sequence 2, 5, 8, 11. Okay, so when you're trying to identify a pattern in the sequence so that you can predict what the next two terms in the sequence are, one of the most basic things to do is to look at the difference between the terms. So 5 minus 2, for example, is 3, 8 minus 5 is 3, and 11 minus 8 is 3. So right away we see that it appears that the sequence is just adding 3 each time. So then in that case, we would say that the next term would be 11 plus 3, which is 14. And the next term after that would be 14 plus 3, which is 17. Okay, that doesn't always work, but if you notice that all the differences are the same, then that's a very good indication that's what the intended sequence was. Of course, there may be some crazy sequence that I don't know about that would result in the same terms. So that's why they ask what are the apparent terms, because you don't know for sure unless someone tells you the definition of the formula for the sequence. Okay, so here's another one: 8, 13, 18, 23, 28. So I imagine you've probably noticed that this is increasing by 5, right? 13 minus 8 is 5, 18 minus 13 is 5, 23 minus 18 is 5, and so on. So we're just increasing by 5 each time. So that would mean that after 28 we would have 33, and after 33 we'd have 38 for the next two terms in the sequence. Okay, part C. What if we had 5, 10, 20, 40, and so on? So if we had to identify a pattern here, subtracting and finding the difference is not going to exactly work, because the difference here is 5, but the difference here is 10, and the difference here is 20. The difference is doubling. Okay, so as were the original terms in the sequence. So you're not going to use the difference in this case. All right. So what can we do? Well, when I notice doubling, I like to write it. Oops. I like to break down the terms. Anytime you see a constant, this is a constant multiple, right? This is being multiplied by 2, multiplied by 2, multiplied by 2. So we could think of this first one as just 5, and then the second term is 5 times 2, and then the third term is 5 times 2 times 2, and then the fourth term is 5 times 2 times 2 times 2. Okay, so each time doubling what we had before. So the next term is going to be that number 40 times 2, 5 times 2 times 2 times 2 times 2 4 times. So that's going to be 80, and then if we double that, we're going to have 160. Okay, so the next thing we're going to talk about is taking that recognition of that pattern that we were just discussing to the next level, meaning that we're going to recognize the pattern and then describe the nth term. So we're going to find a sequence, a sub n, with these first 5 terms. So these are going to be, I'm going to start with those same 3 sequences we just looked at. Before I do that, let me just check if there's any questions or comments. And my students, remember, you can also type in a comment to the live chat bar to get bonus points. Or if you're watching the recorded version of this, you can just type a comment below the video. Okay, so anyway, we're looking at the same sequences. So the first one was 2, 5, 8, 11, 14, and so on. And we want to predict what the nth term would be. So when you notice that the differences between the terms are constant, in other words, that this guy is increasing by 3 every time, this is what this means is that the pattern, if we were to graph it, right, the pattern would be linear. So at n equals 1, we would have 2. At n equals 2, we would have 5. At n equals 3, we would have 8. It's going to increase by 3 each time. Now, when we have a linear function, a regular continuous linear function as we've worked with in the past, remember that always follows the pattern y equals mx plus b, where m is the slope or the amount it's increasing each time when you go up 1 unit. So in this case, we could think of it as our a sub n is always going to be that slope m times the sequence, the term number n, or position in the sequence, plus, I don't know, some number k that happens to be like the y-intercept. Okay, so what we're going to do then is, in this case, I know that a sub n has to look something like 3n plus some number k. So let's consider when n is 1. Remember, this 2 here is the first term in the sequence, so that means a sub 1 is equal to 2. So if I know that, and I also know that a sub 1 equals 3 times 1 plus k, then we can figure out what k must be. So we have 2 equals 3 plus k. Subtracting 1, we get k equals negative 1. So I'm suggesting that the nth term of the sequence would always be defined by 3n minus 1. Now let's just check to see if that works out. So for example, a sub 1 would be 3 times 1 minus 1, which is going to be 2, and that was what we had. A sub 2 is going to be 3 times 2 minus 1, which is 6 minus 1, or 5, which was the second term. And a sub 3 would be 3 times 3, or 9 minus 1, which is 8, which is the third term, and so on. So when you recognize that you have the same difference between the terms, we can easily write a linear pattern for our nth term, and this would be the answer. A sub n equals 3n minus 1. Or if you want to write it as not the nth term, but I guess they asked us for the sequence, so really it would be more appropriate to define the entire sequence. And that just means putting the set brackets around it. Okay. Remember that we also looked at in the previous example the sequence 8, 13, 18, 23, 28. So this was another example where we had a constant difference of 5 in this case. I'm running out of room here. Constant difference of 5. So each time the terms increased by 5. So in that case, that's like having a slope of 5. So you know that your a sub n is going to be 5 times n and then plus some number k. So to figure out what k would have to be so that your first term would turn out to be 8, we look at a sub 1. 8 is equal to 5 times 1 plus k, so k would be positive 3. So our sequence appears to be an equals 5n plus 3. Now this method only works, again, when you have the sequences, the terms are increasing by the same amount each time, giving you that line pattern. Okay, let's look at one where that doesn't happen, our part C from before. I'm just going to erase part A here. Okay, so for part C, we had 5, 10, 20, 40, 80, and remember we observed that it was doubling each time, and I said, notice that that means that we're taking 5 and then we're taking 5 times 2, and then we're getting 5 times 2 times 2, although I'm going to write that as 5 times 2 squared gives you 20. And then for 40, we have 5 times 2 to the third, 5 times 8. Because we're doubling each time, we're increasing the number of factors of 2. So in the next one, we're going to have 5 times 2 to the fourth, right? Okay, so what you want to think about in this case is just matching up the term with its position. So this is the first term. This is n equals 1. For n equals 1, we want to get 5. For n equals 2, we want to get 5 times 2. For n equals 3, we want to get 5 times 2 squared. For n equals 4, we want to get 5 times 2 cubed. And for n equals 5, we want to get 5 times 2 to the 4th. So notice that the power, this is supposed to be a 4, is 1 less than the position. The power on the 2 is always 1 less than the position. Okay, in fact, you might not see it, think about it this way originally, but even the 5 is being multiplied times a 2 to the 0 power, because 2 to the 0 power is 1. So, in general, we have our nth term of our sequence is going to be 5 times, now not 2 to the n, because 2 to the n would have given us 5 times 2 for the first term and 5 times 2 squared for the second term, and so on. We have a power 1 less, so we're just going to say 5 times 2 to the n minus 1. And if we want it to be the whole sequence and not just the nth term, all you do is put in the brackets to symbolize that. So that's another example of how you find the nth term of a sequence. I'm going to check on our chat status here. Looks good. Okay, so the next thing we're going to do, look at this sequence. Find a sequence a sub n whose first 5 terms are 2 over 1, 4 over 3, 8 over 5, 16 over 7, 32 over 9. So often when you have fractions like this, you kind of just think of it as 2 separate sequences. So we're going to try to find an expression that would give us the pattern in the numerator, and then an expression that gives us the pattern in the denominator, keeping in mind that we need to match up that pattern with, n is 1, n is 2, and so on. So let's write down the numerator and the denominator as a separate sequence. So if I had just given you 2, 4, 8, 16, 32, what might you have noticed about that? The differences are not consistent, right? The difference is 2, this one the difference is 4, this one's 8. The differences are doubling. So what that indicates is that these are multiples. These are doubling, actually, each time. We started with 2, and then we had 2 times 2, and then that number doubled, right? And then that number doubled. So each time the number of factors of 2 is increasing. So you could think of this as 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, and so on. So now we match up with our n, right? So n, when n is 1, we have 2 to the first. When n is 2, we have 2 to the second. When n is 3, we have 2 to the third. So we have a pretty clear pattern here. In the numerator, we're just looking at a 2 to the n sequence. Now let's look at the denominator. So the denominator was 1, it had a 1, a 3, a 5, a 7, a 9. Let's look at the differences. The differences consistently are 2's. So that means it's going to follow that linear pattern that we discussed before. So you know your a sub n is going to have a slope of 2 essentially. So you're going to have 2 times n plus some number k. And then we're going to figure out k by looking at a sub 1. So a sub 1 is just 1. And if you plug in 1 for n, we get 1 equals 2 plus k, so k is negative 1. So our a sub nth term over here is 2n minus 1. Okay, if you check, you see if n is 1, you get 2. If n is 2, you get 3, and so on. All right, but this wasn't the whole sequence we were looking for. In fact, let me call this b sub n and b sub n just so we don't get confused. This is just the sequence in the denominator down here. So what we need is our a sub nth term to have a numerator of 2 to the n and a denominator of 2n minus 1. And putting it in the little curvy brackets means we're describing the whole sequence and we're done. Okay, how's everybody doing? No questions so far. Looks like the stream is going well. Okay, so the next thing we're going to do is talk about factorials. So many of the sequences that we are going to look at are going to involve multiplying 1 times 2 times 3 times 4, or 1 times 2 times 3 times 4 times 5, or a whole sequence of integers increasing by 1, actually natural numbers increasing by 1 each time. And so we have a notation, a shorthand notation. You know how we love our shorthand notations. So for example, 5 factorial is just 1 times 2 times 3 times 4 times 5. Your calculator actually has this function on it. It depends on which calculator you're using, where that's located. For example, if you're using the TI-30X2S, then you're going to go to the PRB menu. So you would type 5, you'd hit the PRB button, and then you would underline the exclamation mark, the factorial symbol, and hit enter twice. And you would get, let's see, what's that going to be? 20 times 6 is 120. Okay. 0 factorial is defined to be 1. And it's important to know that the factorial only affects what's immediately in front of it unless there are parentheses. This is just like with exponents. So if you have 2 times n factorial here, what we're saying is just take that 2 out front and multiply it times n factorial, 1 times 2 times 3 times 4, all the way up to n. So for example, if it was 2 times 5 factorial, you would have 2 times 1 times 2 times 3 times 4 times 5. So that was 120, so we would get 240. Very different number from if we have them in parentheses. So if you have 2 times 5 factorial, of course you need to do what's in the parentheses first. So you have 10 factorial, which is a much larger number. 1 times 2 times 3 times 4, all the way up to 10. Let me grab my calculator here. Okay, so trying to see if I have it on this calculator. Oh yeah, here it is. So 10 factorial is 3,628,800. Very big, much larger than 240. So it's real important that we recognize the correct order of operations. All right, so that's what factorials mean. So sometimes in order to work with a sequence, we're going to have to simplify some expressions that are written in terms of factorials. For example, part A, we have n plus 1 factorial over n factorial. All right, so all you have to do is to remember, let's do this with a more concrete example first. So let's suppose we had 6 factorial over 5 factorial. All right, so 6 factorial is just multiplying 1 times 2 times 3 times 4 times 5 times 6. Let me close that. And then 5 factorial is 1 times 2 times 3 times 4 times 5. So what ends up happening is all of these cancel out and we're just left with a 6. All right, so similarly here, I don't know what n is, but I know I'm going to have 1 times 2 times 3 times all the way up to n times n plus 1. And then below that, I have 1 times 2 times 3 all the way up to n. So all of these are going to divide out, leaving a factor of 1. 1 times n plus 1 is just n plus 1. Okay, so that's going to allow us to simplify some sequences, and also when we start talking about their limits and convergence, that'll help us a lot. All right, so the next example, n factorial over n plus 2 factorial. So in the numerator, we have the product of 1 through n. And in the denominator, we have the product of 1 through n, but also we keep going, n plus 1, n plus 2. So everything from n on down divides out, and we're just going to have 1 over n plus 1 times n plus 2. Okay. Now, here's a trickier one. Part C, we have 2n minus 1 factorial over 2n plus 1. Ugh. Getting too close to the bottom of the screen. I think I'm going to have to erase and go back up. Okay, so for part C, we have 2n minus 1 factorial, and we have 2n plus 1 factorial. Okay, so I always find it easier to think in terms of the pluses on these factorials. So let's start with the bottom first. So in the denominator, we're going to have 1, we're going to have 2, we're going to have 3, all the way up to 2 times n, and then 2 times n plus 1, 1 greater than that. Okay, now, just so for purpose of comparison, what would the factor just before 2 times n be? If we could squeeze that in there. Notice it'd be 1 less than 2n, right? So let's go ahead and include that one, because it'll make our lives easier here in a minute when we have to talk about 2n minus 1. So this is going to be 2n minus 1, 2n, 2n plus 1, right? Because remember, we're going up by 1 each time. Okay, and then in the numerator, I have 1 times 2 times 3 all the way up to 2n minus 1. So everything from 2n minus 1 down is going to divide out, and we're just going to be left with 1 over 2n times 2n plus 1. Okay. All right. So we've talked about how to find a formula for the nth term of a sequence in a couple different circumstances. We've talked about how to graph a sequence and how to deal with factorials. And now let's talk about the limit of a sequence. So for example, here we have the sequence 1/2, 1/4, 1/8, 1/16, 1 over 32. It's defined by 1 over 2 to the n. Notice that this is getting smaller and smaller and smaller. So what happens is it actually gets very, very close to 0. So we say as close to 0 as we want. If we wanted to get within, say, 1/1,000,000th of 0, we just have to pick a large enough term in the sequence, a large enough n value, and we can guarantee we can find one that's within that distance from 0, and we could find one that's 1/1,000,000,000th away from 0, as close as we want to get. So it converges to 0. All right, what this is looks like visually, of course, this diagram here on the right is supposed to represent a sequence of values. it doesn't matter what happens at the beginning of the sequence, but if after a finite number of terms, we're always within this band of blue here, epsilon is just talking about the distance from the value of this term in the sequence to the value we think it converges to. So L is the limit. In the last example, when we said it converged to 0, 0 would have been our L. And we have, we say that when I said it, we could get as close as we wanted to 1/1,000,000th or 1/1,000,000,000th away from 0. That's the epsilon that we're talking about there, the distance away from L. We can pick any tiny little epsilon, and we'll see that eventually, at some point in the sequence, all the terms end up within that band of blue there. So terms will lie within the band between y equals L plus epsilon and y equals L minus epsilon. This is very similar to the definition of a limit that we had for functions in Calculus 1. Okay, but it's all about getting closer and closer to a particular value. We can actually compare sequences to continuous functions. So these sequences have discrete input values, right? Not continuous, not a range of values, but individual integers, 1, 2, 3, 4, and so on. The functions that we found limits of in the past did not, but as it turns out, if you can find a function, like let's say we had some function that that graphed something like this. I'm supposed to be hitting those dots though, and I'm not. Hold on. Okay, so we have this function, and each of the terms in my sequence actually hits that function. If we can find the limit of that function, if this is f of x, if we can find the limit as x goes to infinity of f of x, then we can also find the limit as n goes to infinity of a sub n. We can figure out what value the sequence is approaching by finding out what value the function is approaching. So that's really powerful because, for example, if we had a sequence where the nth term was defined to be 1 plus 1 over n to the n, if you recall, the limit as x approaches infinity of 1 plus 1 over x to the x turned out to be e. We proved that in class. So you can just say, well, since this basically fits the same pattern at any value n, the corresponding x value, we could plug in and get the same y value, or how can I put this? In the sequence here, we have an input n and an output a sub n, and in the function here, we have an input x and an output y. And even though we have a lot more values of x and y, whenever x is equal to n, a sub n is equal to y. So their limit is going to be the same, and we can say, well, the limit of the a sub n's is going to be e. And we know that it converges based on what we know about the function. That also allows us to use things like L'Hopital's rule and the powerful tools that we use for functions, other functions, for sequences. Hold on just a moment, please. Okay, sorry about that. Let's see, I'm checking on how our stream is going here. Looks good. Nobody has said they can't hear me, so hopefully you can. Let's see. looks like the volume's working. Okay, so moving along. All right, so now we're going to talk about how to find the limit of a sequence in a couple different ways. Of course, some sequences don't have a limit. They don't converge, they diverge. And they can diverge by approaching positive infinity or negative infinity, or just oscillating. The properties of limits of sequences is going to be very familiar from properties of limits. So if you know that a sequence A sub n has a limit L, and a sequence B sub n has a limit K, then you can conclude that, for example, the limit of A sub n plus B sub n is just L plus K. Or if you have the limit of a constant times A sub n, it's just going to be the constant times L. If you have the limit of the product, you can multiply the product of the limits. And if you, same thing with a quotient, as long as we don't have our denominator equal to 0. So those are just some tools we can use to calculate limits. Another thing that we can use is the squeeze theorem for sequences. We've had a squeeze theorem for functions. So let's look at this graph here. We have, in pink, we have the sequence 1 over 2 to the n plotted out. Remember, this would be just like the function 1 over 2 to the x, or 2 to the negative x, except it just has discrete values instead of a continuous span of values. In blue, we have the function negative 1 over 2 to the n. It's the mirror image of the pink function down there. And then in black, we have negative 1 to the n over n factorial. And so what we see in this diagram is that if we plot negative 1 to the n over n factorial and kind of look at where it lies with respect to the pink and the blue graphs, at first it's outside of the two, but eventually it's between them. And in fact, in general, the expression negative 1 to the n over n factorial is going to be less than 1 over 2 to the n and greater than negative 1 over 2 to the n, as long as n is large enough. So in this case, n had to be, let's see, 1, 2, 3, 4 or larger, looks like. So if n is greater than 4, this is going to hold. There's an explanation in your textbook about how to prove that, but I'm not going to spend a lot of time on that in this lecture. But I just want to point out that if you can show that a function is squeezed between two other functions, and you know the limit of the bounding functions is going to 0, for example, then the limit of the other function is squeezed between 0 and 0. It has to be 0 as well. We've talked about this for some trig functions in the past, and it works for sequences as well. All right, so I'm going to skip this part. All right, another thing we need to remember is something that's very helpful. If you have a sequence a sub n, and you know that the limit as n goes to infinity of the absolute value of the sequence, in other words, the positive version of the sequence, is 0, then that must be meaning that the original sequence converged to 0 as well. All right, so I didn't want to change here. Okay, so what we mean by this is for example, if we have some sequence that is oscillating positive, negative, positive, negative, positive, negative, okay, but the absolute value of that sequence, which would look something like this, okay, would just be all positive versions of those values. If that absolute value sequence is approaching 0, then that must mean that the overall sequence is approaching 0. Because if these absolute values, the positive numbers, are getting within, that small distance of 0, that epsilon away, then that must mean that on both sides of the positive end, when we allow them to be both positive and negative, it's still getting within that same distance of 0. So this is another way we can, sometimes it's easier to work with the positive version of a sequence if we want to find the limit. So you want to keep that in your back pocket as well. Okay, we already talked about how to, We already talked about how to find a formula for a sequence, and this was a sequence that we looked at a minute ago. In addition to finding the a sub n formula for this sequence, I also want to talk about how we could determine whether the sequence converges or diverges. So remember that we said that we could compare the sequence a sub n equals 2 to the n over 2n minus 1. We could compare it to the function f of x equals 2 to the x over 2x minus 1, because they coincide, right? Whenever x and n are the same value, your y or your a sub n is going to be the same. So we're going to use techniques that we already learned to find the limit of the 2 to the x over 2x minus 1, and then we'll conclude that our limit must be the same for our sequence. So how do we do that? Well, we have the limit as x approaches infinity of 2 to the x over 2x minus 1. Notice that if we just tried to plug in right away, the numerator would go to infinity and the denominator would go to infinity as well. This is an indeterminate form, but it's one for which we can use L'Hopital's rule. So what we can do is just take the derivative of 2 to the x in the numerator, which is 2 to the x natural log of 2, and the derivative of 2x minus 1 is just 2. And then from there, we see that, okay, natural log of 2 and 2, these are just constants, right? So we're multiplying, So we're multiplying 2 to the x times some number, but when you allow the exponent to increase without bound, then that means that 2 to the x is going to go to infinity. So this guy is going to infinity. Infinity times natural log of 2 over 2 is still infinity. So we see that this limit's approaching infinity. In other words, the function is divergent. Okay, now according to theorem 9.1, that means that the sequence is also divergent. So we're instantly able to use L'Hopital's rule to help us with determining convergence of sequences. Okay, so let's look at some other sequences and see how we could determine their limits if they exist. So we're going to start with number 25 there, or sorry, 21. So we're going to we're going to just think of this as the function 5x squared over x squared plus 2. So for number 21, if we took the limit as x approaches infinity of 5x squared over x squared plus 2, what will we get? So if you recall way back when we learned about horizontal asymptotes, we learned that when the degrees are the same in the numerator and denominator, when you just have polynomials in the numerator and denominator of equal degree, that we can just look at the coefficients of the highest degree term. So 5 and 1 then, 5 over 1 is going to be just 5. A more algebraic approach to that would be to actually multiply out 1 over x squared in both the numerator and denominator. Okay, so in that case, if you use that approach, what would happen? You'd have, I'm going to switch to black ink here, you'd have the limit as x approaches infinity of 5x squared over 1x squared, so 5, over x squared over x squared is 1 plus 2 over x squared. So taking the limit as x goes to infinity has no effect on the 5 or the 1, and then this guy right here is going to go to 0. So that just gives us 5 again. So that's another way to think about it. Okay, similarly for number 22, by the of the sequence and of the function, right? 5x squared over x squared plus 2. Both of them have the same limit. All right, so number 22, we're taking the limit as, I'm just going to write it as a sequence. The limit as n goes to infinity of 6 plus 2 over n squared, because I know I can apply the same rules I do when I have x going to infinity. So this term is going to go to 0. 2 divided by infinity goes to 0, gets very, very tiny. So this is going to be 6 plus 0, or 6. For number 23, okay, you can say the limit as n goes to infinity of 2n over the square root of n squared plus 1. So again, even though there's a square root, we could think of these two as having the same degree, because the square root of n squared is just n. And you can think of just looking at the coefficient of the highest degree terms, and you would have 2 over 1 or 2. If you wanted to do it more algebraic approach, you could take the limit as n goes to infinity. We're going to multiply by 1 over n, because the highest degree power in the numerator is 1. So 1 over n to the first power. Now in the denominator, yes, I'm going to multiply by 1 over n, but remember I want to put it inside of a radical. So I'm going to think of it as 1 over n squared inside a square root. N is positive, by the way, so we're not going to get an absolute value there. So we're going to have the limit as n goes to infinity of 2n times 1 over n is just 2. Bringing this 1 over n squared, distributing it throughout the radical there, we have n squared over n squared, which is 1, plus 1 times 1 over n squared is 1 over n squared. Okay, so as n goes to infinity, the constants stay the same. This guy goes to 0, and we just have 2 over 1, or 2, which is what we thought we were going to get. Okay, let's go to number 24 now. Throw a little trig function in there. So for number 24, we're taking the limit as n goes to infinity of the cosine of 2 over n. So this is a composition of two continuous, smooth, differentiable functions. So what we can do with this is just think about what's the limit as n goes to infinity of 2 over n. So as n goes to infinity, this guy is getting very close to 0. It's approaching 0, which means that the whole expression is approaching cosine of 0. The whole thing is getting very close to cosine of 0. Remember, cosine of 0 is 1. So that sequence is approaching 1. Okay. All right, we're going to work a few more where we decide whether the sequence converges or diverges. And then we're going to talk about monotonic sequences and bounded sequences. So just real quickly, how can you tell that whether this first sequence converges or diverges? Well, that's just like saying what's the limit as n goes to infinity of the sequence, right? So as n goes to infinity, what's happening is we're getting 5 over infinity, which is approaching 0. So we would say that this guy converges. Okay. On the other hand, for a sub n equals negative 1 to the n times n over n plus 1, let's just list out a few terms here to understand what's happening. So what's happening is we have 1 over 1 plus 1 is 2, and then we have, and that one is going to be negative for a sub 1, because to the first, the negative 1 is to the first power. If we have a sub 2, we have negative 1 to the second power, we get a positive 2 over 3. And then a sub 3, we're going to get a negative 3 over 4. And a sub 4, we're going to get a positive 4 over 5. Okay? Let's keep going, because I think it'll be a little bit more clear if we just keep going. So let's do a couple more. A5 is going to be negative 5, 6. A sub 6 is going to be a positive 6 sevenths. Okay, so what I want to point out to you is if you look at just the negative terms, let me get a highlighter. So just looking at this negative 1/2, negative 3/4, negative 5, 6, we notice that the terms in yellow here are getting closer and closer to negative 1. In fact, let me go ahead and just plot those. So you would have, if this is our graph, there's negative 1, positive 1. So when n is 1, we're at negative 1/2. When n is 3 actually, we're down a little closer to negative 1. When n is 5, we're down even closer to negative 1. It's decreasing closer to negative 1. Those are the yellow terms, the odd numbered terms. Okay, but let's look at the other terms. Okay, so let's color in blue here. When n is 2, we get 2/3, then 4/5, then 6/7, and we can see that it's actually approaching, those blue terms are approaching positive 1. So, oops. So we have 2/3, we have, 4/5, and we have 6/7. So this is increasing just very slightly, and it's getting closer and closer to positive 1. Now remember, in order for a sequence to converge, it has to be getting closer and closer together overall towards some value. But what's happening here is that the top values are getting closer to 1, and the bottom values are getting closer to negative 1. They're getting actually further apart. So this is an example of a divergent sequence. It diverges. Okay. Two paths diverge in a wood. And they're getting closer and closer, each of them to a particular number, but not the same number, so that's not a limit. All right. How about this third? So that was this one. This one's divergent. And how about 10n squared plus 3n plus 7 over 2n squared minus 6? So as I mentioned a few minutes ago, you can take the limit to infinity, and remember that when you do that, you're just going to be focusing in, oops, way too dark here. When you have the same degree terms in the numerator and denominator, you're going to just focus in on the coefficient of those terms. So this one is going to actually converge to 5. Converges. Okay, let's look at natural log of n cubed over 2n. So when you throw natural logs in there and you want to determine if it converges, just remember that we have rules of logarithms. Rules of logs could possibly help. And we have L'Hopital's rule, perhaps could help. So I'm going to go ahead and just to simplify this a bit, I'm going to recognize that that's 3 times the natural log of n there over 2n. All right, or in other words, that's 3 halves times the natural log of n over 2. So the limit is going to be 3 halves times whatever the limit of the natural log of n turns out to be, over 2. Over n, excuse me. Let's fix that. Oops. Wake up, pen. There we go. All right, so I'm going to not set equal. I want to take the limit as n goes to infinity of 3 halves natural log of n over n. Now, if you try evaluating at this point, you're going to get n is going to infinity, and so natural log, when you plug in larger and larger numbers, you get larger and larger numbers. And here, this is unbounded as well. So this is an indeterminate form, but it's one where we can use L'Hopital's rule, LH. So what are we going to do? We're going to keep that 3 halves, because we know it's just going to be 3 halves times the limit. But it's going to be the limit as n goes to infinity of, instead of that indeterminate form, let's take the derivative. So the derivative of natural log of n is just going to be 1 over n, and the derivative of n is just going to be 1. So the limit as n goes to infinity of 1 over n is going to be 0. 3 halves times 0 is 0. So this guy converges. Okay, and one more. We have a sub n equals n plus 1 factorial over n factorial. So in these cases, it's good to simplify if you can at all. Remember, factorial means 1 times 2 times 3 times 4, etc., all the way up to the highest number, in this case, n plus 1. And then in the denominator, we have 1 times 2 times 3 times 4, all the way up to n. All right, so we need to see the n in the numerator so we can get an idea of what's going on. So remember, right before n plus 1, the term before that would have been n. So everything up through the nth term is going to divide out. So really, a sub n is just n plus 1. And if you take the